We're going to continue our discussion of three-dimensional surfaces by looking at a group of surfaces called the quadric surfaces. In two-dimensional space, we have the quadratic curves, also known as the conic sections, and we get these by taking combinations of x and y squared, as well as linear combinations of those, and adding them together. In three-dimensional space, we're going to have the quadric surfaces, and these are going to be made by taking combinations of x squared, y squared, z squared, as well as linear combinations of those variables. So a quadric surface is going to be one that is defined by a second-degree equation. In particular, x, y, or z, at least one of them occurs raised to the second power. Typically, they'll include more than one of those. And in Calculus 3, we generally don't look at surfaces that involve cross terms. In other words, ours are not going to involve terms that have things like x times y or y times z or x times z inside of them. We're going to look at several major families of these, including the ellipsoids, the hyperboloids, the elliptic paraboloids, the hyperbolic paraboloids, and cylinders. And we'll see that in order to identify them, we're going to look at the equation, and we're also going to examine their traces. The traces will look like familiar two-dimensional quadratic curves. We'll have four key things that we're going to be keeping an eye out for as we examine these. The first is which variables are squared. Then we're going to be examining the signs of the squared terms. We'll be checking for the presence or absence of linear terms, and we'll also be looking to see if we're missing any variables. All right, here's a very lengthy list of quick identification tips. So each tip on its own is quick, but the list itself definitely not quick. All right, first, if our equation can be arranged so that we have x squared plus y squared plus z squared, and there may be coefficients around those, equaling a number, all of them are positive, that's an ellipsoid. If one of them is negative and we can arrange things so that the right-hand side is a 1, then that's a hyperboloid of one sheet. If two of them are negative when we set it equal to 1, that's going to be a hyperboloid of two sheets. If we rearrange it and instead of getting a 1 on one side, we get a 0, and the left-hand side contains any negative signs, then we've got an elliptic cone. If one of the variables is linear, in other words, there's an x or a y or a z that isn't squared in there, then we have a paraboloid. I'm not sure I'm pronouncing that right, but I'm going to roll with it. Once we know we have a paraboloid, then if the squared terms are added together, it's an elliptic one. If the squared terms are subtracted, it's a hyperbolic paraboloid. And then remember, of course, that if you're missing a variable, what you have is a cylinder. All right, let's take a look at some examples and see if we can identify these. So here we have an equation. We've got x squared plus y squared plus z squared equals 9. So we can see everything's squared and all of the terms are positive. So this is going to be an ellipsoid. Let's look at, we're going to find its intercepts and its traces. So the intercepts, we're going to have 3 of them, potentially. So to find the x-intercept, we're going to let y and z both be 0. Well, that gives us that x squared is 9, which means that x is positive or negative 3. So we have 2 x-intercepts at the point 3, 0, 0. And negative 3, 0, 0. For our y-intercepts, that means we're going to let x and z be 0. And that is going to give us that y squared is 9. So we have 0, 3, 0, and 0, negative 3, 0 as our y-intercepts. And then for z, hopefully you're seeing the pattern, x and y will be 0. So we get that z squared is 9, which means that z is plus or minus 3. And so we get 0, 0, 3, and 0, 0, negative 3 as our intercepts. Now let's take a look at the traces. So remember we have 3 of those as well. Let's look at the xy trace. The xy trace, we're going to let z be equal to c, some value of c. So that's going to give us x squared, and we can pick a value. Let's let z be, I don't know, let's let it be 1. We'll just pick 1. X squared plus y squared equals, or plus 1 squared equals 9. So that's x squared plus y squared equals 8, which we know is a circle, which of course is an example of an ellipse. So we see that the xy trace is an ellipse. This is a circle with center 0, 0 and radius square root of 8. And then we can look again at, let's look at the xz trace. So then we're going to let let's let y be 1. Just picking 1, I can pick any number I want, but of course now I'm going to get x squared plus z squared is equal to 8, which is again going to be a circle, and that circle is going to be in the xz plane parallel to the y-axis. And probably you can see here, if we do the yz trace, now we let x be a number, and again here we'll have y squared plus z squared equals 8, and we once again have a circle, which is a very specific type of ellipse. And so we can see that the traces are directly related to the name of the surface. The traces are ellipses, and we got an ellipsoid. We can use Desmos to help us figure out what this actually looks like. And so when we plug that in there, we get this surface here, which is actually a sphere. So maybe you already recognize this as the equation of a sphere, but it is in fact a sphere. Remember that all of our traces came out to be circles, which makes sense in the fact that this is a sphere. All right, next example, we have z is equal to y squared, or x squared plus y squared. So notice here that the z term is not squared. So when we have one linear variable, that tells us we have a paraboloid. Still not sure I'm saying that right. Paraboloid, paraboloid, I don't know. Pick your favorite. And when the two terms, the square terms, are added together, that tells us that this is going to be an elliptic paraboloid. So now let's find our intercepts and traces just like we did before. So we'll find the intercepts first. So to find the x-intercepts, we're going to let y and z be 0. So we're going to get x squared is equal to 0. So our x-intercept is that point right there. For the y-intercepts, we're going to let x and z be 0. And so we'll get y squared equals 0, which is the same point we just got. And for the z-intercept, we're going to let x and y be 0. And guess what we get here? Z is 0. So our only intercept here for our elliptic paraboloid is the origin 0, 0, 0. Now let's look at our traces. So if we do the x, y trace, we're letting z be 0. We get 0 equals x squared plus y squared. Well, that's just a point. That's just the origin or intersection. Let's actually change that. Let's not pick c to be 0. Let's pick c to be c. So we get c equals that. So this is a circle, which again is an ellipse. It's a circle with radius square root of c. Let's do the x z trace. So now I'm going to let y be c. So this was let z be c. I'm going to let y equal c. So I get z is equal to x squared plus c squared. Well, that is a parabola. It's a parabola parallel to the y. It's in the xz plane parallel to the y plane. And so it's a parabola. And then if we do the yz plane, so now we're letting x be c, we're going to get z equals c squared, that's constant, plus y squared, which is again a parabola. So we see here that our traces, we got 2 parabolas and 1 ellipse. The fact that there's 2 parabolas is what makes this a paraboloid. The fact that there's 1 ellipse is what makes this an elliptic paraboloid. Here is what our elliptic paraboloid looks like. So you can see that if you were to slice it parallel to the xy plane, you would get a circle. And if you were to slice it parallel to either of the other planes, you would get a parabola. All right, for this one, we have everything squared, but we have one negative sign with two key important things here. We have one negative sign, and we also have this thing equaling 1. So in that case, this is going to be a hyperboloid of 1 sheet. Okay, so let's do our intercepts. So for the x-intercepts, y and z are 0, so we get x squared over 4 equals 1. So x squared is 4. And so our x-intercepts are 2, 0, 0, and negative 2, 0, 0. For our y-intercepts, we're going to get y squared over 9 equals 1. So y squared is 9, y is plus or minus 3. And we get 0, 3, 0, and 0, negative 3, 0. For this one, when we let x and y be 0, we get negative z squared equals 1. That has no solution. So we have no z-intercept. We're not going to cross the z-axis for this one. Now let's take a look at our traces. So we get our y trace, letting z be 0, we get x squared over 4 plus y squared over 9 is equal to 1. Well, that is an ellipse. So it might, at this point, kind of be a mystery why this is a hyperboloid. But now let's do the xc trace. So now we're going to let y be 0, and here we get x squared over 4 minus z squared is equal to 1, which is a hyperbola. And if we do the yz trace, letting x be 0, we get y squared over 9 minus z squared equals 1. Again, a hyperbola. So we can see that the preponderance of the traces are hyperbolas, and that is why this thing is a hyperboloid. When we take a look at its graph, we'll see why it's a hyperboloid of 1 sheet. So looking at this shape on the left, we can see that it sort of has two parts, but they're joined together, which is the part where the 1 sheet definition comes from, when the two hyperbolic pieces touch each other. And if you look at the view on the right, that's a top-down view showing that this does in fact not touch the z-axis, which we saw when we looked at the intercepts. Okay, hopefully by now you've gotten a hang of finding the intercepts and traces. So for this one, we're just going to examine the equation, and we're going to see if we can identify the surface. So we've got a couple of things that are important. We've got a negative sign here and another one here. So we have two negative signs, and this thing is adding up to equal 1. So that tells us that this is going to be a hyperboloid. But the two negative signs mean that we have 2 sheets. And we'll take a look at this and see what it means to have 2 sheets as well. So you can see here that the two pieces of this hyperboloid are separate from each other, which is why it's called the hyperboloid of 2 sheets. All right, in this next one, we've got all 3 squared. But we don't have it equal to 1 or 0, so let's rearrange it. We're going to rearrange this as x squared over 4 plus y squared over 9 minus z squared. When we do that, we get equals 0. And even if we cancel out those denominators, we're going to get a 0 on the right-hand side. So that tells us, because we have 1 minus sign right here, and we have equals 0 here, that this is going to be an elliptic cone. So if we look at two particular traces of this, we can see that the elliptic cone is slightly different than the hyperboloid of one or two sheets. And in particular, let's look at the XZ trace and the YZ trace, but in particular the XZ trace when Y is 0 and the YZ trace when X is 0. So instead of just letting it be an arbitrary value of C, we're going to in particular pick the traces when X and Y are 0. So for the XZ trace, when Y is 0, we get that X squared over 4 is going to equal Z squared, which means that X squared is 4Z squared, and we can square root both sides of that to get that X is then plus or minus 2Z. And the key thing here is that this particular trace is not a hyperbola anymore, it's a line. And that's what's going to be the key difference in the elliptic cone. Same thing over here, we get Y squared over 9 is Z squared, which means that Y squared is 9Z squared, and we get the lines Y equals plus or minus 3Z. That's a line. And so the elliptic cone has two traces that are going to be straight lines rather than hyperbola. And here is what that is going to look like. Again, from the graph, not super easy to distinguish from the hyperboloid. So you have to look carefully at the traces or notice that the hyperboloid can be rearranged to be equal to 1. The elliptic cone is going to be rearranged to be equal to 0. All right, one last one here. We've got X squared minus Y squared equals 16Z. So our key feature, one of our key features here is that Z is linear. We also have subtraction here. So we know that when one of the terms is linear, the linear is going to suggest or tell us that we have a paraboloid, the one I'm really struggling to pronounce. The subtraction is going to tell us that that is hyperbolic. We're not going to do the traces. You can do them on your own, but what this would mean is that one trace is going to give us a hyperbola, and the other two traces are going to be parabolas. And this is what that hyperbolic paraboloid would look like. All right, our wrap-up summary. So quadric surfaces are the generalization of the quadratic curves that we see in 2 dimensions to 3-dimensional spaces. Second-degree equations are how we're going to recognize them, and that's what's going to determine their shape. So we'll have to have at least one of x, y, or z squared in order to be looking at a quadric surface. And we saw, as we worked through the examples, that the traces are essential for both visualizing what the surface looks like and as well as identifying it. So the names come from what the traces look like. So, and there's a summary there of the quick tips that hopefully with a little bit of practice, you will start to be able to recognize these surfaces pretty quickly.